Hello, quick video on algebraic division. We may be presented with a horrible polynomial like this one here, a fifth order, there we are, x to the power 5 there, and we may want to fully factorise it and break it down, and by using factor theorem, which we did the other day, and also algebraic division, we're able to do this. So let me take you through an example. Okay, let's start with this cubic function here, and if we remember from our factor theorem, the basis of factor theorem is that if I put a value, in this case 1, x equals 1 into the function and the answer comes out at 0, then x minus 1 is a factor of the expression, and in this the function. In this case, let's just say an x equals 1, that's 1 minus 4 minus 7 plus 10, yep, so that's 0, isn't it? It's going to equal 0, yeah. So what we've proved is that this function can be broken down into this linear factor, x minus 1 times by g of x, which is some other function which has got all the other parts of this in. It could be multiple brackets. And what we're going to do now is use this method, the algebraic division, to find what g of x is. Okay, algebraic division, well, it looks just like the full long division. So we've got our expression here, our function for the x cubed, the cubic, and we're going to divide it. In fact, you're going to chunk it up into lots of x minus 1. Okay, so the first thing we want to do is to deal with this x cubed, and we want to work out how many chunks we can have there, how many multiples of x minus 1 we can get within x cubed. Well, here we can see that we take our x minus 1, and what we're going to do, well, we're going to multiply it by x squared. If we did that, we'd have an x cubed, but we'd also have a minus x squared, yeah? So we know that our first multiple here is x squared, and I put the x squared in the squares in the powers of 2 column, yeah? And because I know that, I effectively can take that chunk off. So if I take that chunk off, I'm left over the remainder is, well, I've got no x cubes because I've used all of those, and I've got, I'm going to put in white here, excuse me, I'm just going to do this in white. I'm going to be left with minus 4x squared, take away a negative x squared, so I'm going to be left with a minus 3x squared left over in our remainder. Oh look, I've got 7x still, I've not done anything with that, and I've got my 10. Okay, but I've dealt with all my x cubed, haven't I? So let's have a look at what I can do with my x squareds. Well, how many multiples of x minus 1 go into this, particularly into this minus 3x squared? Well, I can do minus 3x multiples of lots of x minus 1 would give us that term there, wouldn't it? So that's minus 3x squared, and that will cancel that out. We can take that off, but that also means that I've got this minus 1 term over here, so that means that I've got a plus 3x there. So that would be, that's the amount of that, isn't it? And I'm going to take that off because I've now dealt with that. I'm just going to write that up here in the x's column, power 1 column. So I've taken, now I know that I've got minus 3x, lots of that in there. And again, if I now look at what my remainder is, well, I've got no x squareds left, but I've got minus 7x, and I've taken off another 3x, so that's minus 10x here, plus 10. So that's what I've got left over at this point. That's my leftover. So what can I do next? Well, I want to get rid of that. And so how many x minus 1s can I get into that? Well, I think we can see that we can get minus 10 of those in. So that's our units. So I'm going to put minus 10 there up at the top. And if I multiply this over there, if I multiply and bring it over, I get minus 10x there. And I get plus 10 there, don't I? Because that's the minus 1 times minus 10. And if I now take that off, I find I've got nothing left. That's my remainder, isn't it? That's my remainder equals 0. Well, that's what I would expect, isn't it? Because we'd already proved that this was a factor, so we shouldn't expect there to be a remainder. So there we are. We've proved that we can take this cubic up here, this cubic, and if we divide it by x minus 1, that's that linear factor, we find that our answer is this quadratic there, x squared minus 3x minus 10. And we've just done that using ideas we probably did at in junior school, really, isn't it? Chunking and multiples, and using that for long division. Okay, so let's just go down. I'm going to put up on the screen a more nicely written out one there so you can see it. There we are. I'm going to leave it for a sec, so if you need to, you can stop the video and copy that down. Okay, so what have we proved? Well, we've proved that that cubic expression can be rewritten as this factor x minus 1 and this quadratic expression there in this bracket. Now what we want to do is to break that that quadratic expression up, and we can either do that by having another go at factor theorem and look for a factor, or we could use our quadratic knowledge and just look for using the adding and multiplying approach. And we could quite quickly down here see that x squared minus 3x minus 10 could be factorised into x plus 2 times x minus 5. Yeah, because those two multiplied together give us minus 10, and those two added together give us minus 3. And therefore, we fully factorised this expression into these three factors. And that's what we wanted to achieve, yeah? So we used the factor theorem and algebraic division once we found one factor to move the cubic down to a quadratic. And if you think about it, we could do exactly the same thing with a fifth order, bring it down to fourth, third, second, quadratic then, and then solve that way. So we can do exactly the same thing for a higher order polynomial. Okay, so here we are. Quick summary on the screen. We can use algebraic division from with a known factor, and we get that known factor from our factor theorem, and then we can just divide it using this method. So there's our cubic divided by that x minus 1 linear gives us this quadratic here. There we go. That gave us that quadratic there, and therefore we quickly showed that that one equals x minus 1 times that quadratic, and we can use this approach over and over again until we've fully factorised any polynomial. Hope that's of use.